In this video, I want to show you how to calculate power in electrical circuit elements. Let's sketch a generic circuit element. Let's assume that there's some current flowing through it, and then some voltage across it. So notice that no current is complete without a direction, and no voltage is complete without a polarity. So we need the arrow with a direction and the plus and minus to specify the orientation of the voltage. Now we can calculate the power delivered to any circuit element using the following very simple equation. So we need to point out and make clear that this is the voltage across the element with a polarity. So it has a well-defined direction. And this is the current flowing through the element. While this equation looks very simple, I must give you a warning. There are many ways to get this wrong. So the current and the voltage that you use must be consistent. So how do we make sure that we remain consistent about our calculation? Well, the answer is the passive reference convention. So we always follow the passive reference convention. What is the passive reference convention? That states that the current should flow through the circuit from the plus side of the voltage to the minus side. And so that's exactly what we have up here is this current, or the plus node of the defined voltage polarity first, and then flowing through the device to the minus side of the with polarity as defined. Another way to say this is that it's the current flowing in the direction of the voltage drop. That is from plus to minus. The way to handle it if this isn't the case, that if our current and voltage don't satisfy the passive reference convention, the first way actually is just to use a minus sign. We'll put here A. There's another option. We've got option A, option B. A is the simpler one, use the negative sign. B is actually equivalent, and we just change the current or the voltage so that we have something that follows the passive reference convention. And you'll see how these are the same. Let's do a couple of examples. The first example will be the easiest. Let's have a voltage source and a resistor. Now we know how this goes. This first node, let's call it A, is higher than the second node, which we will call B. And A is higher than B by 5 volts. That's what the voltage source tells us. Now the voltage across the resistor, well, it's also VAB in this direction, right, with B as the reference and A as the observation point. And what does this mean? That means that the current flows this way through the circuit because the resistor is passive, so current will flow through the resistor from the high node to the low node. And let's write this as I. And using Ohm's law, it's going to be 5 volts per 1 kilo ohm. Notice I'm going to be careful to use the passive reference convention. Again, I actually put it in another video, which I'll link in the description. But this works out to be 5 milliamps in the clockwise direction. Now you can see that if I were to calculate the power delivered to the resistor, it would look like this. PR. Notice that the current and VAB follow the passive reference convention. So I can use I, which is 5 milliamps, and the V, and I get 25 milliwatts. One thing to note is that P greater than 0, so positive power, means that power is delivered to the resistor. That's why we wrote up here calculate the power delivered. What does the resistor do with this power? It dissipates it as heat. On the other hand, if power is less than 0, an element supplies power. That's because if you look back at this, we're calculating power delivered to any circuit element. That's to say, power is the rate of energy poured into the element, but if that rate is negative, then that element actually supplies power. So the resistor receives 25 milliwatts of power. Now we can look at the battery or the voltage source, because we know that 5 milliamps flows this direction and 5 milliamps this direction. But notice that in the case of the power supply, this does not follow the passive reference convention, because the current is flowing from the minus terminal to the plus terminal as it goes through the circuit. So for the voltage source, it's a little different. Here, we have to use P equals negative VI. This is method A, where we just use the negative sign. So we have a negative, and then V is 5 volts, and I is 5 milliamps. So now we have negative 25 milliamps. So that means that the voltage source supplies power. And it should make us happy, it should satisfy us that the resistor receives all the power that the voltage source supplies. Okay, next we'll try method B, which is to find a current or voltage to satisfy or follow the passive reference convention. Well, how can we do that? We know that 5 milliamps flows upward through the voltage source. So we can equivalently say that there's a current of IR for reverse, and that I is negative 5 milliamps, right? It's exactly opposite of the 5 milliamps that we know goes clockwise. But with the sign and the direction, it makes it this IR actually equivalent to I. And now notice that IR, in fact, follows the passive reference convention now with the battery or voltage source, because it enters the plus side and leaves the negative side. So for option B, we'll just use the regular P equals VI, but the question is which V are we using? And so it's VAB. And which I are we using? That's another important question. And this is the IR. VAB we know is 5 volts, and then IR is negative 5 milliamps, and it's negative 25 milliwatts. And I see that in the upper answer I need to change the units, it's milliwatts. But notice here that both options A and B are consistent because they're both predicting negative 25 milliwatts of power delivered to the voltage supply, which is the same as supplying power. One last example to look at. Let's suppose we had a 6-volt battery, 6-volt source, resistor, 3-volt battery or voltage source. Let's just say, for example, that this is a 3 kilo ohm resistor. It's going to turn out that we have 1 milliamp of current flowing this way. And that is how that will work. Let's call this first battery EA, and then this one will be EB. So E is for electromotive force. Let's calculate the power delivered by each of these items. So power delivered to the resistor, suppose that I tell you that it's 3 volts. 3 volts from across the resistor. How can I know that? Well, let's say that this node is going to be the high node. Let's call it A. This one will be B. This one will be C. Without assigning concrete numbers to any node, we know that A has to be 6 volts higher than C, and B is 3 volts higher than C, meaning that A to B must also be 3 volts. So A to B is 3 volts. We'll label that VAB. Now we can do this. We can see that this 1 milliamp flows counterclockwise, and it's consistent with the passive reference convention for the resistor, right? It's going from the plus side to the minus side. You can write VI, V being 3 volts, I is 1 milliamp. So again, it makes sense. It's positive, so this is received power. For battery B, we have 1 milliamp of current. You can see that it's not following the passive reference convention. So I will change it so that it's negative 1 milliamp. That follows the passive reference convention with the voltage of the battery. So that negative 1 milliamp flows from positive to negative. So we'll write this as VI, again being 6 volts, I being 1 milliamp, negative 1 milliamp that should be, so negative 6 milliwatts. So battery B is supplying 6 milliwatts of power. Battery A now, we know that there's 1 milliamp flowing this way. That current and the voltage, in fact, are consistent with the passive reference convention. So we'd put here it's 3 volts and 1 milliamp, right? Because the resistor and battery A are receiving power because their power we calculated is positive. Battery B is supplying. Notice that battery B is supplying both battery A and the resistor, and the supply is equal to the demand. So it all adds up to 0. That's the conservation of power. And so what does it mean when a voltage source is receiving power? Well, it might mean that the battery is charging. Okay, so in summary, use P equals VI if you're following the passive reference convention, or use P equals negative VI if you're not following the passive reference convention. The alternate method is to reverse one of the currents or the voltages so that it does follow the passive reference convention. The two ways I showed you to handle the non-passive reference convention cases are actually equivalent. Okay, so I hope that helps you become aware of and know how to handle the signs for power calculations.